Hello, everyone, and thank you for joining today's Slang virtual meetup. In today's session, we will attempt to explain the underlying mental model for how Slang reflects shader code and how to use the Reflection API to access the information that developers most often need. And our speaker today is Teresa Foley, one of the co-creators of the Slang language and senior staff engineer at NVIDIA. But first, a couple of housekeeping items. If you have any questions during the presentation, please ask using the Q&A feature located on your Zoom toolbar at the bottom of your screen. We are recording this webinar and we'll post a link to the recording on the Slang website. At the end of the session, please complete the short survey to help us better design future events. With that, I'll hand it off to Teresa Foley, co-creator of the Slang language. Tess?
So as Jeff said, I'm Tess. I'm here to talk about the Slang Reflection API a bit today. And I hope you're all ready to learn. If there are those of you on the session today who've maybe interacted with Slang before and tried to get this Reflection API working, I want to acknowledge that some of you have run into some difficulties with it, got confused about it. This is one of the most frequent causes of concern we hear from users of Slang. And so I really do want to start the presentation off by saying it's not just you. This part of the Slang API is very tricky to learn and understand. We've seen this complaint from users a lot. So it's good for us to be having sessions like this to try to help everybody get on the same page about how to use it. And if you haven't used the Slang Reflection API before and are wondering why would it be so difficult, well, there are a couple of different reasons why reflection in Slang is a slightly complicated problem. Some of that complexity is just necessary complexity, right? We're building a shading language that tries to cover a bunch of different target platforms and graphics APIs, and they all have very different binding models, or sometimes subtly different binding models, but important differences. And we're also working with a much more advanced and capable language than something like GLSL or HLSL here. So there are more interesting, complicated abstractions in the source language that affect how things get transformed into code for the graphics API, and therefore affect how reflection has to show what happened. So for these kinds of complexities, I'm going to claim that understanding the mental model of the Slang Reflection API will help you a lot. And that's the goal of today's talk in particular. On the other side, some of the complexity in the Slang Reflection API is historical or accidental complexity. We've been working on this same compiler code base for almost a decade now, starting in the days when it was a research project. And actually the code itself, we were using in some research projects before. So this code base has been alive for more than a decade. And we've actually managed to have very few breaks in source and binary compatibility over years of deploying Slang now. So we've kept a lot of cruft in there just to keep old applications working that are based on Slang. And as a result, that means there are some parts of the API that honestly you just shouldn't use because they're just there to support old applications. And so if you've seen this meme before, the idea that here's all of JavaScript and then here's this much smaller book on the good parts, the talk today is really the start of this. We recognize that there's a lot of code to the Slang Reflection API. It may not make sense why all of it is there. So instead, we're going to start talking about, hey, here are the good parts. Here are the parts you actually want to use. But at the same time, even just those good parts is a lot of material to cover. So as I was preparing for today, I started realizing I had 2 to 3 hours worth of material and had to cut it down to something that would actually fit in today's session. So just for today, all this talk is going to cover is sort of fundamental concepts and building blocks that the Slang Reflection API is based on. And so if you want to have more sessions like this that do deeper dive into the Reflection API, use the survey feedback, let us know what you want to hear. And then if there are things that come up in Q&A today, or you have specific problems in your code base that you want to get help on, I'd like to just go ahead and switch over to Discord when this session ends. I think we're going to try and open up one of the voice channels on the Slang Discord server. Hopefully somebody else on the Zoom meeting can help you get a link for joining the Discord if you're not already on it. I'll switch over to Discord after this call and try to be available for as long as I can stand, just being there to answer questions or help with specific issues in people's code or interactions with the reflection API. So if you came here because like you have this one specific problem and I don't get to it, let's talk on Discord right after this call, okay? So with that kind of preliminary matter out of the way, what we've observed in most code bases that deal with shaders and do reflection is that their use cases fall into one of two very broad camps. So the first of these camps is kind of the reflect everything camp. So you compile your shader and then you want to run some code on it that's just going to exhaustively extract every bit of information the compiler is willing to give you about that shader. Very often these are things that copy the information from the compiler's format over to some application or engine specific format. And then your runtime queries will often be based on your application's representation of reflection information. The other camp are applications that maybe are willing to use the Slang reflection API more closely coupled with how they're doing rendering. And then they have these very task specific kind of queries they want a reflection API to answer. So it might be something where it's like, you have this texture over here and you have this descriptor set over here, and you want to know, well, where do I plug the texture in there? It's my diffuse map. Which binding does it go into? Or you just compiled a shader and you know you need to create descriptor set layouts for it because you want to create a pipeline layout for it so you can render with Vulkan. What should go into them? Please tell me. So these two use cases end up being fairly distinct in terms of what they actually want from a reflection API. And so for today, we're just focused on that first case. If your use cases are in that second case, great. We'd like to talk to you more about that. We're not going to have time for that today. We've had to scope reduce quite a bit to get to what we have here. So we're focused on this first case where your goal is just to take a shader and reflect every single bit of information about it that you can. And I'm going to talk about scratching the surface of that. We're not going to get very deep. And that means that some of you are going to want to move a little faster than I do. And it's also possible that some of you are coming on this call and have not used the Slang reflection API before, maybe haven't even used the C++ Slang API to compile things before. And so this might go too fast or too slow for you. So if you want to learn at your own pace, the material I'm going to cover today is completely just a subset of what's already in the user's guide for Slang. So the first URL on this slide is a chapter of our user guide, all about how to use reflection to exhaustively pull the information out about shader parameters. And that chapter itself is based on an example program I wrote that is in the Slang codebase in the repository. That's the second URL on this slide. And so you can use that codebase as a reference for how to do this kind of reflection. A lot of the material on my slides is effectively going to be copy pasted out of that and the overall flow of that. So you can have that open in another window to try to cross-reference what I'm doing. Or again, if this pace is not right for you, you can learn at your own speed using those resources. So if you do open up that second link, the example there, you're going to find that that example shows how the big picture of just getting all the reflection information out from Slang is actually pretty simple. You know, it's just organized as a set of mutually recursive functions. Now that application is just trying to print all the reflection information, not copy it into some other data structure. So it just has functions to print the entire layout of a program or an entry point or a type or a variable. So it seems deceptively simple to just write the same function that that example has. But the reason that example can keep its code fairly concise is that it has the right mental model. And so it's really important, and what I'm going to cover mostly today is how to get your mental model of reflection as a task and shader reflection aligned with the way the Slang API likes to think about it. And so that's really our topic. If you're hoping for getting in more into the nitty gritty of all the details of the API, you're probably one of the people that wants to just grill me with questions on Discord afterward. But today we're going to talk about what is the mental model for how to think about reflection in Slang. And at the high level, one of the first points I want to make, just because some of you probably have experience with other reflection APIs for shaders, is that a key difference between Slang and a lot of other systems is that Slang reflects the input program that you wrote, not the output of compilation. And to get a little more crisp about that, there are some reflection APIs out there that focus on the output of the compilation. So if you're using SpearV Reflect already, or if you're in the D3D world and use the ID3D12 shader reflection interface, those are both output-oriented reflection APIs. They have different queries for each kind of target-specific construct. SPIR-V-reflect gives you a different function to enumerate your descriptor bindings, your varying outputs, your specialization constants, and so forth. So it's all oriented around the target-specific constructs that are the result as the output of compilation, if that makes any sense. So as a result, these APIs are kind of fundamentally target-specific. They're not portable, and that was already a no-go for Slang. We can't really have target-specific reflection APIs for every single target we support. Another consequence of the output-oriented nature of these other reflection APIs is that they give no information for parameters that aren't statically used somewhere in your code. So if you don't use a texture, it just doesn't show up in the information that SPIR-V-reflect gives you. And that means you as an application author can't tell the difference between, hey, I looked up this string and it wasn't there. Does that mean there is no parameter with that name, or it just isn't used? In contrast, the way that Slang does this is that Slang reflection focuses on the input to the compilation, the program that you actually wrote. So the structure of the reflection data and how you navigate it is in terms of the constructs that are actually in your program, your entry points, your functions, your types, your variables. And so everything is about how the code you wrote is structured, and then you find out via reflection what target-specific construct each piece of your program was mapped to. So you can kind of think of these as inverse views. One is looking at the output and explains what part of the input it came from, and one is looking at the input and telling you where in the output that went. And so if you don't align yourself with that worldview, you're probably going to end up a little confused. Along those lines, I want to now talk about what the key building blocks of Slang reflection are. And they're really these four types, these four constructs here. So on the left side of this slide, we have types and type layouts. And on the right side of the slide, we have variables and variable layouts. And I've written the type that actually appears in the Slang C++ reflection API under each of them, but those names are a little more verbose than I want to put on slides, so I'm just going to use the shorter names in the boxes for most of this. And a lot of people who are new to the Slang reflection API get frustrated that there are these very discrete granular constructs on this slide. They say, hey, why can't I just say, here is my parameter, how big is it, where is it, and what other parameters is it made up of if it's a struct? Why do you break it down in this kind of way? So I want to describe why the pieces of information on this slide are the right ones for actually reflecting shader code, and why they kind of give you the right semantic model for what's going on in your code. So focusing on different parts of this at a time, I want to just look at the bottom two items, type layouts and variable layouts. And a key thing to have in your mental model when interacting with Slang is that type layouts really represent size information, and variable layouts really represent offset information. So anywhere in the reflection API you see a variable layout, think this may not actually represent a real variable in the program. It's there because we need offset information. And if there's a type layout, it's a context where we need size information. So to get really concrete about this, if you have some code like this, we declare a struct for some of our parameters, and then we stick it in a constant buffer, right? That's going to apply some layout to that code. Maybe it applies std 140 if you're compiling for SPIR-V output. And that's going to determine the layout of the fields that struct. And in particular, that field B, the second one, the int B, is going to have a layout applied to it. And that layout can really be broken into two distinct pieces of information. On the left side, there's a type. Its name is int, and then the layout for it gives it a size of 4 bytes. And that's type layout information. And on the right, if we actually look at the variable, its name is B, and its offset is 16 bytes into the overall struct. Right. And of course, there's a connection between these two, which is that the variable on the right has a type, and that type is the type on the left-hand side. And so the reflection data is always structured like this. Variable layouts have type layouts, but they are distinct things. Right? You can query the size of a variable, but really you're querying the size of the underlying type of it. And if you want to structure your code in terms of sort of recursively pulling all the information out from Slang reflection, what you're going to see is that this same structure on this slide turns into a relationship between these two functions in your actual code. So this is code kind of copy-pasted from that example, where maybe on the left, we want to be able to print out the information about a type layout. And on the right, we want to be able to print out the information about a variable layout. But that function for printing out a variable layout is going to delegate to the type layout. It's going to make a recursive call into the type layout printing logic, because that's the part that actually knows the type of the variable and all the information about it. So we can reuse all that code by connecting these two functions together. Now, getting back to our high-level picture, the other distinction I want to draw is if we look at just the left side of this slide, we have both types and type layouts. And the question again can arise, why? Why does the reflection API need two things to represent types? And the key thing to understand here in your mental model is that in every major GPU shading language, HLSL, GLSL, and Slang, the same type can be laid out in more than one way. So to get concrete about this again, if you define a type for your vertices, this extremely simple type here, the type reflection information for something like this is just going to say, well, the name of it is vertex, this is a struct, and here are its fields, right? But that same vertex struct type can be used in many different ways in your shader code. Maybe you put it in a structured buffer and then fetch from that. Maybe you fetch one of them from a byte address buffer. And then maybe you actually use this vertex type as the output from your vertex shader. And each of these three different use cases is going to result in a different layout for this type. So there we have three different type layouts based on the same vertex type. On the left, for the structured buffer case, it's going to use something like std430 layout and get this size of 32 bytes with 16-byte alignment. In the middle case, if it's loaded from a byte address buffer, it's effectively going to use something like scalar layout, and so the size is going to be 24 bytes with 4-byte alignment. And then on the right, if it's used as the output from your vertex shader, that struct now occupies two of your varying out locations with an alignment of one location, not that the alignment matters in that case. So what we see here is that there can be multiple type layouts that are all based on the same underlying type. And again, that shows up in the structure of how you'd write the code for an application that fully extracts all the type information. You're going to end up needing distinct functions for extracting the information from a type, like the function at the top here, and extracting the information from a type layout, like the function at the bottom. Right? In the type case, you don't have any size information you can print. Just given a type out of nowhere, you can't actually know how it was laid out, and so you don't know what size it is. Is it the 24-byte case or the 32-byte case? If you have a type layout, though, you can print size information, and so you get a lot of the same information in these two cases. The name is still available, and in fact, most of the queries you can make on a type layout are really just accessing information about the underlying type and then adding size information to it. So hopefully that helped fill in the relationship between these sort of four fundamental constructs in the reflection API to give you a better idea of why we broke it out this way, right? If we look at the arrows pointing to the left here, a variable has a type, a variable layout has a type layout. And if we look at the arrows pointing up, type layouts are based on types, variable layouts are based on variables. All right. The next really big picture concept that I want to make sure I get across is the idea that types can have their size measured in different layout units. So it's not very useful when you're doing a shader compiler to ask about the size of a texture 2D in bytes, right? That's not how that type is measured. So it's important to understand that the size or the offset of a variable, the size of a type or the offset of a variable could be measured in these different layout units. I'm using this word somewhat abstractly, but think of like units of measure. So if we go back to that same vertex type that was defined before, right, the type reflection information, we showed this before, is the same for that type no matter what, but we can have different layouts applied to it. And what I want to call out here, the same type again, is that two of these three layouts use bytes as the unit of measure for how big the type is. The third one actually uses a different unit. If you're using something as the varying output of your vertex shader, it consumes locations, not bytes. And that is how the sizes of things are computed. That's how size limits are defined via the API. And so the Slang reflection API will correctly report the usage of the correct unit for that type. Its size is measured in a different way. What's more, it's not just the different the size and offset can be in these different units on a per type basis. A single type can actually consume more than one kind of unit. It can have a size that needs to be measured in multiple units. And this arises a lot for advanced Slang programs because Slang encourages you to start thinking semantically about how you want to organize your data. Instead of organizing all my textures go over here and all my uniforms go over here, Slang encourages you to group together logically related parameters. So if we had a struct to represent information about a light, this is obviously greatly simplified, but if in your engine you had a representation of lights that needs direction and intensity information, but also every light can have a shadow map, the right way to express this in something like Slang is group all that information together in the same type. Just because textures get bound differently than vectors doesn't mean they aren't logically related in terms of the modularity of your program. But then if we go to try to measure this type for a certain kind of layout algorithm, we're often going to find that the size of this type needs to be measured in both bytes and bindings, right? If you put this in a structured buffer, or a constant buffer with std 430 layout, you might get that the size of the type is 24 bytes. I guess scalar layout in that case. You might get the size of the type is 24 bytes plus one binding. There needs to be something measuring that the texture is there. And there's no way to turn this into just a single unit. You can't measure the texture in bytes and you can't measure the vectors in bindings. You really do need these two different layout units. Now, those of you who've actually tried to use the Slang Reflection API might be wondering where this phrasing of layout unit is coming from. I'm using that term because I hope it actually makes sense to everybody. But in terms of the actual API header file, the thing I'm calling a layout unit is in slang.h called slang parameter category. And that name is just extremely confusing. Nobody who uses Slang Reflection seems able to intuit what in the world that's supposed to mean. All I can say is I'm sorry. I don't exactly know what I was thinking when I introduced that name. If you go open up the header file and look at that enum, what you're going to notice also is that there are just a lot of cases there. And part of this is because the Slang API needs to cover a lot of different target platforms and APIs. And what's more, we try on the project to only reuse the cases in that enum if the semantics align between different platforms. So an example there is that Web GPU uses almost all the same enum values that Vulkan does because their binding models align really well. They're almost semantically equivalent. But D3D uses some different values than Vulkan because it turns out that the D3D binding model, and especially how it measures things, is different than Vulkan. So we can't use the same enums because the semantics are different. So depending on what target you're compiling for or what targets your application needs to care about, you're only going to encounter a subset of the values in this enum. And we're going to get to the details of what you're likely to see when compiling for Vulkan in a little bit. But now that we've actually talked about the basic mental model, you have this idea that, okay, a type can have more than one unit in its size, and different types might be measured in different units. Now we can actually talk about some actual reflection API details. Here's how to query the size and offset of types in the Slang Reflection API. And my hope is that now that we've covered so much mental model, the actual code is not going to look that complicated anymore. So if you're using the Slang Reflection API, it's important to know that the default unit is bytes. If you just have a type layout and you ask it for its size or its alignment, it's going to give you size or alignment in bytes. If you have a variable layout and you ask it for its offset, it's going to give you the offset in bytes. The only really interesting detail to note here is that if the size returned by the get size operation is, hexadecimal FFFFFF, then that means that the size was unknown or unbounded. It's not the cleanest API for returning that information, but again, we've maintained this compatibility across a lot of generations, and we didn't have unbounded size arrays earlier on. So apologies again for that bit, but just be aware of that. If you get a size that seems way too big to be true, that may be this unbounded case. So again, if you just query size or alignment of a type without any extra parameters, you're asking in bytes, just like anybody would do for maybe if you had reflection for C or C++, this is kind of what you would expect the behavior to be. Now, if you know exactly which unit you want to query, then it's also pretty simple. So if I have a variable representing the layout unit, and again, it's used in this parameter category enum, if I know the unit I want to query, I just pass that in to the get size or get alignment operation. or the get offset operation on the variable layout. These queries are now going to give the size of that type in the particular layout unit. And if it's a layout unit that type doesn't use, you're going to get 0. But if it's a layout unit that type does consume, it's going to tell you how big it is in that specific layout unit. It's worth noting that the alignment call is kind of a little silly to have here. Things in Slang, the alignment is always going to be 1 if the layout unit is not just bytes. There's really no such thing as complicated alignment rules for other kinds of units, at least not that we model in the reflection API. So you don't really need to save off information about alignment for other units, but it's there for completeness, just in case you want to query things in a very orthogonal way. So that covers 2 cases. If you just want bytes, really easy. If you know exactly what layout unit you expect a parameter to occupy, also pretty easy. The place where people get tripped up using the Slang reflection API is back to this thing of types can use more than 1 layout unit. And if you're just exhaustively scraping all the reflection data, you also may not know what layout units you expect a type to consume. You've just got this type and you're asked to say, how big is it? And how big is not a really well-defined query in terms of any one layout unit. You need to query all of them, it would seem. So that's where the last bit of the reflection API around sizes and offsets comes up that has confused a lot of people. So if you don't know what to expect, if you don't know what units this type might consume, we have these 2 additional API calls on a type layout, and there's equivalent ones on a variable layout. So you can ask with this query called getCategoryCount. Again, category is a terrible name. Think of that call as saying, how many layout units is the type measured in? How many layout units should I query to figure out how big this type is? And then the getCategoryByIndex is helping you iterate over them. So this loop on this slide is just the way to iterate over, here are all the layout units where this type might have a non-zero size. And then we query the size and alignment for each of those units. The actual call to get the size and alignment is the same in all of these cases. And it's really just that in this case, we put a loop around it and say, hey, for all the layout units that are interesting for this type, what is the size and what is the alignment? And there's equivalent calls for variables. So I hope that progression helps explain some of the complexity in the API here. Again, we're trying to make sure that this reflection API can account for the general case. And in the general case, a single type might occupy storage in multiple different layout units at once. And so the API needed to have this level of flexibility to let you query all the details about sizes. All right, moving on, still about this topic of layout units, but just getting into some details if you're programming for Vulkan. I'm assuming everybody on this call is at least a little familiar with Vulkan or uses Vulkan as one of the graphics APIs you target. And there's probably some of you for whom it's the only graphics API you're really concerned about. And so if you are compiling using Slang for Vulkan, what subset of this layout stuff, these layout units, do you need to care about? So this slide has a little table that is trying to be kind of a decoder ring for, on the left, here's what I would call human readable description of what the layout unit is. And on the right is the value of that parameter category enum that describes that layout unit. And so you can see these are the main cases that you will see in your Vulkan program. A lot of things are measured in bytes. The stuff inside constant buffers obviously is a big example. Your descriptor bindings are going to use this type called, or this enum value called descriptor table slot. The descriptor sets themselves are typically going to use this thing called sub-element register space. I apologize, that's another weird name. Varying in locations use varying input, varying out locations use varying output. At least those ones are pretty easy to understand. And then push constant ranges and specialization constant IDs also get cases here. So it's a much smaller subset than the full enum. And I partly bring up this slide to say, these are the ones you're going to see. And now I want to talk about some gotchas that people run into when they try to use the Slang reflection API for their Vulkan renderer or their Vulkan application. So these are real kind of problems we've seen people run into, and I want to talk about each of them just in case they're biting you. The first problem we see people run into is that they try to query their Vulkan shaders using certain cases that are D3D oriented. So some of the values in this parameter category enum have names like constant buffer, shader resource, unordered access, and sampler state. Those of you who have a lot of familiarity with D3D and DX bytecode or Dixel will probably recognize these as B registers, T registers, U registers, and S registers. And that's what the layout unit in those cases is actually representing. So those are very D3D specific layout concepts, and they aren't used in Vulkan compilation. The output of Vulkan compilation is going to use this one type called descriptor table slot, which is used to represent bindings in Vulkan and the equivalent construct in WebGPU. So don't go querying with these other cases and expect it to work. All right. And that does bite some portable applications. Sometimes people want to write the same code for the D3D and the Vulkan case, and they just query using the D3D concepts and get confused why they're getting all zeros out on Vulkan. So watch out for this one if you're writing a D3D12 plus Vulkan renderer. The next gotcha here is around register spaces in this API, which for everybody out here, think of it as the descriptor set indices. So there's another enumerant in the parameter category just called register space. And yes, that's a D3D terminology. They have register spaces where Vulkan has descriptor set indices. But the Slang Reflection API has two different enums that both seem like they're gesturing at the same basic concept. And so a lot of people try to use this one at the bottom called register space. And I just want to be clear here. It's best to think of this as a legacy feature that you should probably completely ignore. It had the wrong semantics for a lot of use cases, but then we had applications that were reliant on the broken semantics. And so we kept it in and added a new value to represent what we think is actually the correct thing. But one other detail to understand there is that this layout unit for descriptor sets, this sub-element register space layout unit, measures what I would call whole descriptor sets. It measures parameters that use up an entire descriptor set index by themselves. So it's not measuring the descriptor set index that is paired with a binding. That's a different concept. So unless you're using Slang parameter blocks, you're probably not running into that case either. So that opens up this question of, wait, how in the world do I actually query the set and binding index with this API? A lot of you probably, if you are writing HLSL code for Vulkan, or if you're writing GLSL, you have very similar style of layout attributes. You probably have code that looks like the first line of code on this slide. You might be using the VK binding attribute to set things up. So in this case, the texture parameter T wants to be assigned to binding 42 in set index 13, just made up numbers here. So in that case, when you're querying via the Slang Reflection API, the layout unit you want to use is bindings, which per that table a couple slides ago is this descriptor table slot case, right? And the correct way to query this with the Slang Reflection API is to use both the get offset call. So at the bottom of the slide, look at those two lines of code. The first call uses get offset, like I've explained before, and that gets you the binding index when you pass in that layout unit. And then there's another operation, get binding space. You pass in the same layout unit and it will get you the set index that pairs with that binding index. And that is currently the correct way to query for cases where you've used a manual binding attribute like that. So if you use VK binding to put things into a binding and set index, this is the kind of query you're going to need to run in your code. But this is where I kind of want to digress for a bit and say that if you're interested in writing an idiomatic Slang code base, if you want to try and take advantage of Slang the most in your code rather than just port your existing shaders over and pretend like Slang is just GLSL or HLSL, I would like to note that Slang doesn't need those manual annotations like existing shader compilers for GLSL and HLSL do. And in fact, the very design of Slang kind of doesn't want those. And that's because when we were designing this compiler, we actually had enough lived experience with large shader code bases from game developers that we'd seen how the use of manual annotations was really one of these things, people talk about a code smell. And for me, manual annotations in a shader code base are one of those. I've seen too many times how they negatively impact the portability and maintainability of shader code. They cost people real time when they're developing shader code base. And really the only reason people are using these, in my opinion, is that they've been forced to by poor language design choices in existing shading languages. So we don't have time to get into all of this today, but I do want to note that Slang supports much better approaches for getting good use of descriptor sets in things like Vulkan, and does so without these manual annotations. It lets you have cleaner, more modular code that is still just as efficient. So that would be another great topic for one of these sessions. But again, don't have time to get into it today. I just want to make sure people are aware there are better ways to do this. The last gotcha that I want to get into that kind of relates to this layout unit topic, but doesn't actually, I've noticed a lot of developers get tripped up when it comes to trying to define the VkDescriptorType for a shader parameter. So the common scenario I've seen people in here is that they're trying to fill out the struct, VkDescriptor set layout bindings. They're trying to build a descriptor set layout because they're trying to build a pipeline layout. And what they have is this Slang type layout for their shader parameter. And they're asking me like, wait, why can't I just query what units this type uses? And then that should tell me what VkDescriptorType to fill in so I can set up my descriptor sets. And that's unfortunately kind of a wrong mental model to apply here. I understand why people want to have an answer to that question, but I just want to make clear that layout units aren't that. And that's because the descriptor type exposed to the Vulkan API has no impact on layout. So they're not represented in the Slang reflection API as layout units, right? And you can tell that they're not something that impacts layout because they don't appear at the sphere V level either, right? The sphere V level just shows, hey, this consumes this binding index, right? So the Slang reflection API does have a way to try to query that kind of information. There's an entirely separate enum called Slang binding type that has a much closer mapping to VkDescriptorType. So you can definitely derive a VkDescriptorType from the information in a Slang binding type. So that's a different part of the reflection API that I don't have time to get to today. This is mostly for reference for people that are getting confused on the like, hey, I want to fill out a descriptor set layout from Slang reflection. How do I do that? And just to give a pointer of like, this is the part of the API you're going to need to look at if you want to get that answer. All right. The last topic that I want to cover as far as mental model on Slang reflection is to start thinking about offsets for shader parameters in terms of relative and cumulative offsets. And this is something that a lot of those existing reflection APIs don't deal with because I talked earlier about the fact that they're oriented around the output of compilation. And that means they have the final baked, like this is the actual set index and binding index perspective. Whereas Slang's top-down perspective means that offsets could be relative or cumulative. So this applies even in languages like C or C++. This isn't a Slang-specific concept. So I just want to point out that if I have types like these on the left-hand side of the slide, maybe I've grouped my camera parameters together, I've grouped some lighting environment parameters together, and then I have a struct for all my uniform parameters that has both the camera and the lighting environment in it. Again, these are always very simplified examples. Don't be surprised if your shader code is way more complicated than what I'm showing. But in this simplified example, we can look at that lighting environment type, and we can say that, the relative offset of this sky color field relative to the start of the environment type is 12 bytes, say, or for whatever layout representation we're using. Maybe this is all scalar layout. The relative offset of the end field within the param struct is 16 bytes. So these are all relative offsets so far. Just here's the offset of this field within the struct type it's part of. But then if I declare some shader parameter params, P of type params, and I want to have like, what is the offset of the sky color field? It is not useful to say the offset of the sky color field is 12 bytes. That's incorrect in the case of this particular variable P. Right, the cumulative offset of p.env.skyColor is, in this case, the sum of those two relative offsets. And so the cumulative offset here is 28 bytes. So the cumulative offset of an actual final leaf parameter depends on the relative offsets of everything kind of on the access path leading to it, right? And it's important to understand this information because the Slang reflection API reports things in terms of relative offsets. So it's always saying, like, in this type, this field has this offset and things like that. And it assumes that your application will take responsibility for calculating the cumulative offsets for itself. And this is made a little more complicated by that thing I mentioned earlier that, well, the sizes of things and the offsets of things can be measured in more than one layout unit. And so it isn't just accumulating a scalar size in terms of bytes and adding it up as you go down the hierarchy. The offset representation needs to be slightly more nuanced to get right answers for this. So there are various ways that you can track or compute the cumulative offsets in your application code. This is, again, one of the, hey, that would be a great topic for another day kind of things. We just don't really have time to get into that level of detail in an introductory talk. But I do want to note that if you go open up that example code in the Slang repository that I referenced earlier, the one that all these slides are kind of borrowing from, that shows one approach to computing cumulative offsets that is pretty simple to implement. And so the code is out there. You can use those as templates to start from. But I just want to make sure that you understand the high level point that Slang reflection is giving you relative offsets and giving you responsibility for computing the cumulative offsets. And another common gotcha for programmers is they somehow expect Slang to give them, cumulative offsets. It's giving them relative offsets, and they say, hey, why are the numbers wrong? And we say, hey, you need to add them up in this way. So be prepared for that if you're running into problems with Slang reflection. There's some nuance here. We should have more discussion about this, but I want to make sure you get the high level. So that's a lot of big picture topics we've covered. Just make sure I summarize so everybody hears this. It may seem like we haven't actually covered a lot because I haven't talked about details of function calls and APIs all that much, but that's because I want to make sure you nail these big picture mental model things, and they may help you interact with the Slang API with a little more efficiency and a little less confusion about why it is the way it is. So the first key point was that think about type layouts as size information, variable layouts as offset information. Try to remember that there can be many different layouts for the same type or the same variable, right? The size of a type is not a meaningful thing because it can be laid out in multiple different ways. And so the size of a type layout is what's meaningful in a shading language. Another key point was that size and offset for shader parameters or shader types are measured in various different layout units. So one type layout can use multiple different layout units, right? So you can have a struct that combines textures and vectors, and its layout is going to be measured in multiple layout units at the same time. And then this last point was that the Slang reflection API is really about reporting relative offsets of fields within structs and things like that. And it assumes that your application takes responsibility for computing the cumulative offsets that it needs. So those are the big picture things we covered today. And it's obvious that there's a lot more we didn't cover. We're having this talk because reflection API was one of the most common things that people answered they wanted to hear more about in the previous survey we did. And there's still a lot more that we could cover on reflection. So we didn't get into the various kinds of types and the specific properties of each. So structures and arrays and matrices and resources all have specific ways that you can query their layout information beyond what's available for the basic case that's available for all types. We also didn't cover the top-down structure of the reflection data. Like at some level, you compiled your shader code with Slang and you have this program and you have reflection information for it. And the question you probably have is, how do I dive down into it? How do I get to all the global shader parameters? How do I get to the entry points and their parameters? And work down to the leaves before I get to these variables and types that I've talked about today. So that's another topic that we could get into in the future. We also haven't talked about this more task-oriented kind of reflection, right? The case where you have some Slang reflection type in one hand and a Vulkan struct you're trying to fill in on the other, and you're trying to get from one to the other, right? Maybe you have the Vulkan struct for a descriptor set layout and some Slang type reflection, and you're trying to say, well, how do I allocate a descriptor set based on this type reflection? Or you have an actual descriptor set and you have a shader parameter with some offset, and you say, well, how do I get which binding in my descriptor set does this parameter represent? these are very real queries that you'd want to perform in an application. And that more task-oriented view is a topic I would like to make sure we cover in the future if there's interest. And then the last thing here, I vaguely said, hey, there's a better way to do your shader parameters than manual annotation for set and binding. We should probably talk about parameter blocks with users who aren't familiar with it yet. It's one of the most important features in Slang as compared to other shading languages. And it's really the way that we allow people to write clean, maintainable, and high performance code that is highly portable across different APIs. So these are great topics I would love us to cover in future sessions if there's interest. So with that said, I want to thank everybody for making time to listen in today. And please do fill out surveys. I don't know who sends around the survey stuff, but let us know with survey feedback what you'd like to see covered next. If you'd like to go deeper into the reflection API, let us know which parts you want to hear more about. If you think this is enough for now and you want to switch gears and cover other topics, also let us know that. And again, if we end up going into Q&A and there's more feedback or more bugs or more whatever than there's time for, come on over to the Discord after this session and I'll try to be available for chat. And if you've come out of this session saying like, wow, this Slang reflection API, I want to make it better. I think I have some ideas. Get involved with us on GitHub. Maybe raise a flag on Discord to let us know you're interested, or just start interacting on the GitHub for the project. We really do want to start building a community around this. And we've had some great contributions from the community already. And there's great opportunities to turn this into the kind of project that would be most useful for the applications you like to write. So yeah, thank you again for your time. And hopefully there's good time for questions right now.
Excellent. Thank you. That was a lot of great information, Tess. Appreciate it. I'd like to invite anyone in the audience, if you have any questions, to please use the Q&A feature located on your Zoom toolbar at the bottom of the screen and submit any questions that you may have. But first, let me ask you a question. If you're advocating for not using explicit location attributes, then what are we supposed to be using instead?
Yeah, so that is this parameter block idea. So there's some information about that in the Slang docs, but one of the key features of Slang, even from the earliest days of the project, was that we wanted to give users a first-class language construct for expressing descriptor sets and descriptor tables in D3D. And what you have in GLSL is very much bolted on of like, it takes the existing GLSL language and puts descriptor set indices on everything. If we have time to do a session on parameter blocks, they really are our answer to that. And I can't really give full justice to it here, but that is the answer. So if you are interested in how to not have to write manual annotations on all your parameters, please do ask to hear more about parameter blocks, or just come talk to us about them and we'll help you understand.
Wonderful. One question I had come in says, does Slang reserve the binding slot for unused parameters? If so, will that be a problem for engines like Unreal that always declare all parameters in their shaders and depend on the compiler to remove unused parameters and compact the binding indices?
Okay, yeah, that's a really nuanced question. And so for anybody who's actually dealing with engines like that, this is actually a good thing to cover. Slang has this philosophical thing that we don't dead code eliminate your shader parameters. And that is in contrast to a lot of other shader compilers. We do that so that the reflection information we provide is stable. So if you're using pound defines for specialization and you toggle things on and off, if all that changed was your function bodies, then Slang provides this fairly strong guarantee that the layout of your shader code, the reflection information, will not change if all you changed was your function bodies. And most other shader compilers don't provide that guarantee. That's great, but the trade-off is exactly this point, is that we don't compact things. And that does create problems for engines that have a high-level architecture similar to Unreal, where they have shaders with thousands of parameters declared, and then they rely on a compiler to compact that down to just the 20 or so, maybe, for particular paths that are actually used. If you have an engine that's architected that way, you may find that integrating Slang is fairly difficult because our philosophy of how to approach things is different. If you are building your architecture for your renderer or your engine more from the ground up, I would encourage people to think about different approaches in Slang. It gets back to the parameter block thing at that point even. There are just different architectural approaches but that is a very real thing. If your engine fundamentally assumes I can throw thousands of shader parameters at the compiler and it will tell me just a compact subset that were used, Slang may not be a good fit for your application.
Okay. Another question came in. How do I use the Slang reflection API to query which stages a parameter is accessed from?
Yeah. So that's another one of those like topics that we didn't have time to get into here. If you're in the slang.h header, I would look up the interface called iMetadata. So there's a little bit of a complication there because, as I keep saying, the reflection API reflects the program that you wrote and gives information that's largely independent of the particular compile, right? It doesn't care what the function bodies were, which means the Slang reflection API proper doesn't actually know whether a parameter was used or not because it wants to be independent of those function bodies. So we have a separate interface provided through the Slang compiler where you can query this metadata on a particular compiled output from Slang. And then you can say, hey, given this location that the reflection API told me, does this particular compiled binary use that or not? So I think it's called is parameter location used. So we have an API for querying that stuff, but it's important for people to understand that there's a distinction then between reflection of the input program versus reflection of a specific compiled output program, which is that metadata interface.
Wonderful. Thank you, Tess. I don't see any other questions coming in, but I just want to let everyone know that we do have a channel set up in Discord. It's on the left-hand side under the list of channels under voice. There will be a reflection API channel set up that we will be joining in probably about 10 minutes. Give us a chance to get some water, and we'll have that open for anyone that has any questions. And as a reminder, a recording of this presentation along with the slides will be available on the Slang website, and a direct link will be sent to you up in a follow-up email. As you leave the webinar, we do have a survey that will pop up. If you can answer that, your feedback is important, and it'll help us improve the presentations and let us know what other Chronos-related topics you'd like to be interested in. Thank you for joining us, and have a great day. Thank you.
Thanks, everybody.